haptic. Okay, thank you. Thank you. And this is a work that is mainly developed by Mustafa Mohammadi, a PhD student in my lab. He was not able to attend. And with my postdoc Davide Barcelli and our friends and collaborator Antonio Franchi from La CNRS. Okay, so the contribution of this work is here summarized. So the idea is to have, let me say, flying fingers that are attached to quadrotors, and they cooperatively go towards an object to realize a flying hand that moves an object. This kind of cooperation comes also from the fact that Antonio is mainly in the quadrotor aerial vehicle control. My expertise was mainly on grasping and tele-operation, so we found proper competence to develop this kind of research. Well, so what's the context? The context is the context of aerial manipulation. Okay, so the aerial manipulation are, on the left you can see one of the flying helicopter that is small, with a small gripper that takes a small object developed by Dollar. On the other side here you see a bigger helicopter developed by the group of Olero with an arm and a hand, because if you want to bring heavier objects, you have to have larger vehicles. Of course, you can scale this problem, and you can still use small quadrotors to move a larger object by using a team of quadrotors. The problem of the team of quadrotors here, especially in this work by Kumar, is in this case that they are using the cables. The cables have two problems. One is that they are flexible, so it's difficult to go while flying to grasp an object. And the other one is that it's a bilateral constraint, so it's not easy to detach and to attach. So in some sense requires some maneuver that is not easy to do while flying. So we want to deal with these two problems. We want to remove the flexible cables, and we don't want not to use the bilateral contact constraints. So our contact mechanism is basically one contact point. So like while I'm grasping this object with my finger, exactly in this way, okay? So it's one unilateral contact between the aerial finger and the object, but is in some sense reinforced by the magnet here. So the magnet has an adhesive force that helps in some sense to have this contact, but it's exactly the same equations of friction constraints. So this is the structure to realize the contact here on one side, and on the other side you see that we substituted the flexible link with a rigid link. Okay, so this is a design that has been developed during this work. The other thing is that, of course, if everything is rigid, it's difficult. When I touch a surface, so I need to have some degrees of freedom. So inspired by the work of Dongjun Lee, last year IROS, we used a spherical joint. This spherical joint is completely passive, so the finger can move freely, okay? But it is locked during the free motion, and it becomes free only when it is in contact with the object, okay? So you will see now a movie when you see the rigid link attached to the quadrotor. How it is detached? Automatically. You see here there is a micro switch, and this micro switch, as soon as I touch the surface, activate a servo motor here on the joint that frees the degrees of freedom, and then the spherical joint is free to move. Okay, so this is the idea. Then the other contribution of this work comes from the literature of grasping and object manipulation. So the literature of grasping and object manipulation is proper for this work because they are, I mean, in our community we were working a lot with unilateral constraints. You don't need this kind of literature if you have bilateral constraints, so if you are attached in some sense to the object. But if you can touch and detach, you need the knowledge of grasping, exactly as we are doing with our manipulating hands, okay? So we took literature and we, okay, just briefly, when you manipulate an object, what you do? You basically want to control with your hand or with these flying fingers, your flying hand, you want to control the motion of the object, the trajectory of the object. And how you do? You do through contact forces. So what is in your hand actually is to control the contact forces between your fingers and the object. But unfortunately, the contact constraints are constrained. So they have to satisfy satisfy friction constraints, magnetic adhesion force constraints, detachment constraints, and other kind of things. So there should be for sure an optimization problem that we have to work on. Okay, so let's have a look at the constraints. So the constraints are, of course, the simplest is on the, so you have constraints on the aerial vehicle and on the contact geometry. So this is a zoom of the contact here. This is the aerial vehicle. You can control this force and you transmit the force and the torque on the object here. So let's go with the spherical joint. And sorry, the thrust constraints. So the thrust constraints, so you can apply a certain maximum force that depends on the power of your thrust, okay, and also a minimum. So it should be greater than a minimum. Otherwise, you have problems. So the force of the aerial vehicle is limited by a minimum and a maximum. The other point is that you have a spherical joint limit. The spherical joint is a passive joint, has some limits, so you cannot freely move. So your force should stay within this cone. And this is due to mechanical limited spherical joint. It's like a friction cone, so your force should stay in this friction cone. And this is the mathematics that explain this this spherical joint limit cone that comes from the mechanical structure. Then you have the object fragility. The object fragility, of course, means that if you apply a force here, then this force is transmitted onto the object, and you don't want to apply too much force, otherwise you break the object. And on the other side, you don't want to detach the object. Then, if there is no magnet, this limit is 0. Because as soon as the force inverts the direction, you detach. I mean, there is no contact anymore. This is a little bit more easy because there is a minus km, minus value, that depends on the magnet force, okay? The magnet adhesive force. So this is the friction, sorry, the contact constraints limit augmented with magnet. Then you don't have to break the contacts, of course, because if you have this is just is not glued, of course. If you apply a force, you can detach with the torque, okay? So this is some constraints on the torques that this force are applying to this surface, and you don't want to detach. And these are balanced again by the magnetic force. Then you have the friction force that is exactly like the friction cone force, but again is augmented by the adhesion force. So the normal force, that is the standard force that you need to evaluate the maximum tangential force that you can apply, is augmented by the magnetic force, this term k. If k is equal to 0, is exactly one finger without any magnets. So the mathematics is ready to go for k is equal to 0. Okay, and again, you can transmit both forces here, the contact, and also rotational torques. So also the rotational torque moment that you transmit at the contact should not slip like this way. And this is some constraint here. Okay, so we have all these constraints, okay? And we have to satisfy, while we control the object motion, all these constraints. So go back to the problem of controlling the manipulation of these objects. So you want to have a certain control, a certain trajectory of the object. So you want to move your object, I don't know, along a circle or some other kind of trajectory. And you want to find now the forces that you have to apply with your aerial vehicles that then transmits to the contact. Okay, so the first equation is very simple. It's so you have the dynamics of the object here, m, b, and g is the gravity force here, the small g. Okay, so this is just simple dynamics. This is interesting. This is the grasping force. So the F vector are the forces that are applied through the thrusts at the aerial vehicle, and then they are mapped onto the object, and they generate a net force effect on the object. So basically, this is a famous matrix in grasping. It's called, in fact, grasp matrix. It's basically when you apply contact forces at your contact points, compute the net effect of these forces onto the object. Okay, so it's basically the control in the central mass of the object. Okay, so you have, in this case, we have F is a 9 vector because you have 3 forces in the first aerial vehicle, 3 components of the force in the second aerial vehicle, and the 3 components of the fourth in the third aerial vehicle. So this is 9. Then there is a theorem in grasping. Of course, it's not so much difficult. That says if you have three points that do not belong to a plane, then you can always apply any wrench to the object. Okay. So also while you do some grasp planning, you have to be sure that you have not to be close to the singularity in order to apply any force. This is important for unilaterality, because if it is bilateral, there is no these constraints. Okay. If it is attached. Okay. Then it's 3 minutes. Okay. Okay. Then we have this. Of course, this is the trajectory control. What we have to do is to try to distribute this force onto the thrust of the single motor. If we do this with the grasping force distribution, the grasping force distribution consists of basically an equality is computed according to the constraints. So you want that your net force is equal to the one that you plan to move the object. Then you have to satisfy all the constraints that I described before, and then there is an optimization. So you want to find an overall contact force that satisfies a small force in order to have the energy low, and also some first order smoothing during the motion. If you realize and you solve, if you state and solve this convex optimization problem, you find the solution and you are able to find this force vector here, that then they are moved to do the attitude and thrust control. That is a classical literature in aerial vehicle control. We use this reference, but basically we just compute the thrust given the total force we want to apply. We orient basically the plane. So this is done. Okay, so this is the slave part. Then we go to the haptic part. The haptic part, I will try to go very quick. So the haptic part is, so there is a lot of literature. Also Paolo and Antonio worked together with Christian Secchi and Bultov on the haptic coordination and control of a team of robots. And there is evidence that haptics is very good in controlling this kind of robot. This is the haptic interface. I don't want to go into these details. What I want to say just is that the force feedback is done by using an obstacle repulsive force that comes from the literature on the aerial vehicle, plus two components that are viscoelastic force. One is a force that brings the end point of the omega at the center of the workspace, because we are controlling in velocity. So a displacement of the haptic display is a velocity. Okay, and then there is also a viscoelastic force here. I'm sorry, where is it? Yes, it's here. The viscoelastic force here that smooths, that get closer to the side trajectory if we are far away from getting the trajectory tracking. Let me show a video. So it's almost experimental. So we have a real robot in my lab running with the rigid. This is the rigid link. This is the contact point with the magnets. There is the spherical point. You can see we are controlling everything. It's not ready yet to do the grasping. We did the simulation. Everything has been simulated. The quadrotor dynamics, the motor, the thrust dynamics. This is the simulation with human in the loop, which means that we simulated this contact interaction, and all the dynamics are here simulated. It's very, very realistic. We are really ready to go in the scenario. We are tracking the quadrotors with a Vicon system, and this using the haptic interface and moving the object from here to the goal. You see that the inequality, the upper bound and the lower bound of the inequality constraints are all of them are negative. The equality constraints, that means that I'm really applying the force is this. And then this is trajectory that is very close to the one that we desire. These are the forces. And also in terms of haptics, we have an improvement. We tested 10 subjects and we saw that without haptics, the performance. So all the subjects have the visual feedback, but when you have haptics, there is a lot of, there is improvement. Conclusions. So we want to go in a real experiments by adding also the passivity layer in the real experiments. Then we want to evaluate also other haptic policy and to improve the contact mechanism to remove the magnet part. And I wish to thank Mostafa, who did most of the job, my postdoc Davide, and the cooperation with Antonio Franchi. Okay. Thank you. We have time for one quick Thank you.
So I imagine that because of the constraints of the contact forces, it can happen that the object cannot move as the master desires it to move. So in this case, what does it feel? What does it feel?
So in this case, since we have three contacts, we don't have any limit in terms of geometry, but just as constraints, like you said. But so we didn't perceive problem with the constraints yet because the friction was high. One of the reasons we use the plate is that the plate is really high friction and we have the magnet. So the constraint is there, but we were not able to perceive. What you are saying is that do some analysis to see what happens if you go, if you overcome the constraints and what happens for the haptics. Yeah. The optimization always satisfies the constraints. So if you don't have the constraints satisfied, you don't get the results in some sense.
But then the master feels it.
The master feels it.
I would like to move in a certain direction that is outside of the constraints.
Yeah.
Somehow I should be able to feel it.
Yeah, but
for example, if I want the slave to go in a linear motion, and because of the constraints it rotates. For example, I expect the user feels a rotation. Yeah. While he's asking for a translation.
Yes, this is true, but this is also a limit of, this is a force device. Now we are, in my lab, we have a Sigma that has also torques, and also the long-term goal is to apply my freehand technologies there. So you should be able to see what happens in terms of rotation, because you had more information on the display, on the haptic display.